Welcome to the third presentation from the Information Systems and Semantics series, which is this time about SPARQL and other practical use cases with RDF. I will again start with a brief recap of the previous presentations, and then I will cover what is SPARQL and how it can be used. Other practical use cases will follow, starting with semantic web, nano-publications, persistent and resolvable URLs. And the final part will be quickly showing how to work with RDF when programming in your projects. So first, to recap, RDF specifies how to describe any resource using triples or quotes in the form of subject, predicate, object, and potentially some context. Such RDF statements can be captured, and we've seen that in different formats, including Turtle, but also, for example, XML, JSON LD, RDFA, and others. To provide semantics, rules, and constraints, we need to actually use some models or metamodels, and usually in the RDF terminology those are called ontologies that define some concepts and relations between them. Such ontologies can be defined again in RDF as we've seen, and basically on all the levels, so on the metamodel level, meta-metamodel level, model level, and then also like the instances the data are as well in RDF. And the last part during the previous presentation was about shapes and how you can check compliance with some rules or constraints by defining these shapes, which are basically some patterns that you expect from the RDF statements. So let's start with SPARQL. It's semantic query language for data stored in RDF format. It's one of the key technologies of semantic web. If you remember the semantic web stack, it was part of that, but we will come to that again today. It is really similar to SQL at the first glance. So if you will see later on the SPARQL queries, you will see some of the same keywords, and you will see that it's really working in the same way. So the transition from SQL to SPARQL is quite simple. But of course, in SPARQL you are working with these triples and patterns instead of with relations between tables. So as I said, there are some patterns, and the querying work based on using these patterns to match some subject, predicates, and objects. And of course, SPARQL is defined or specified as W3C recommendation. You can again take a look at that, and it has several parts. One of them, for example, describes how to make queries in SPARQL. And that's also the thing that we will cover now. And queries can be in one of these four forms, and all of them return some types of result set or graphs. So first one is select, for selecting some data according to the query. And construct is to create some new RDF statements from the existing ones. Ask returns truth value true or false based on the pattern, and describe returns a description of some resource or data matching the query. Let's take a look at each in a bit detail. So first, select one. We have here again the example with if that minces meat. And here you can see that we again need some prefixes. That's something that we know from the RDF formats. And then we are selecting something. Here you can see the similarity with SQL. So we are here looking for name and weight. and we specify what are these variables in the where part of the statement of this query, and we are actually matching that we are looking for a person that minces some meat, and the person has some name, and the name is the bound variable to the select. And then we are checking also the weight of the meat. Moreover, we can use something more than just these patterns of triples, which are basically written in turtle format. And we can use some keywords, in this case filter, and we are stating that we want just those matches where weight is higher than 100 grams. We can also use some additional parts of this SPARQL query, for example, ordering by weight in descending order and limiting to top 10 results. So we will get top 10 as a scoreboard of people mincing some meat. You can really see the similarity with SQL if you take a look at that. Just instead of joining tables in the where part, we are making some pattern matching. Another query form is construct, and in this example we are taking a look at man in our data set that has some name, and we are constructing new triples where we use FOAF ontology, friend of a friend ontology, and predicate name from that ontology. So we are actually doing here some translation from our example ontology to FOAF. So result of this query would be new RDF dataset. From the previous select one, it would be basically table with 2 columns, but SPARQL supports different result sets, so you could export it as, for example, CSV table, as JSON, or as some other format, including RDF again. The third one is ask query, and here we are asking, is there any instance of woman that minces meat? So again, we have prefix, but then we have just ask with the pattern matching. There is no other option to write something more. There is no need to have ordering, limiting, etc. So we have just this pattern, and if anything matches this pattern, the result will be true. If there is no such case, the result will be false. In this case, in describe query, we have a where again, just as we had for construct and for select, but here we don't want to construct something new or get the table of results, but we want to have all the description about the matching resource. So here we want to know all the details about some person, and the name of the person must be Eve. And then the result of this will be actually the subset of the triples in the dataset. Those were 4 queries that you can use to explore the RDF datasets using these patterns, but SPARQL allows also modification of data, including work with quotes, name graph or contacts, and also with multiple datasets. So there are also queries that can insert, delete, and update data, but also work with separate graphs. So you can create, drop, copy, move, or add graph to existing datasets. So you are creating or removing or moving some contacts from the graph, and then in the SPARQL queries you can, for example, limit the search to certain graphs. we've seen also the use of filter keyword, but there are again much more. For example, optional, union, distinct, disjoint, count, etc. Some of them are again very similar to what you know, for example, from SQL. Here you can, for example, see count and distinct, but many of those are working the same way or with the same semantics. What is also important or interesting from SPARQL is that basically when you have some database, but also some service, those expose something called SPARQL endpoint, which is something that you send the queries to and then expect the desired result. And you can actually connect to multiple SPARQL endpoints and use some federated query. So you basically run a query to multiple SPARQL endpoints at the same time and then get some aggregated result. So for example, in this case, we are looking for some person, and then in the other service, we are looking for objects or other people who that person knows. So you can compose queries like that basically use datasets stored in different locations, in different servers, in different services. You can of course run your own triple store and play with that, for example with GraphDB, and fill that with some data and then use queries. But you can also do that with Wikidata, which I already mentioned in the previous presentation. And there is Wikidata query service, and you can try SPARQL there. There are also some examples. And last time we had some example with capitals and countries with this numeric identifiers. And you can, for example, run a query like that, and you will see all capitals of all countries as a table. But possibly you can also do some of the examples that are there, and you will see that Wikidata can present some results, for example, on a map or using some charts. That was for SPARQL, and we can see that SPARQL is also part of the semantic web technologies, just as all RDFS that we covered last time. And basically now we covered most of the technologies that you can see here in the stack. But actually, how you represent RDF in semantic web, we touched that during the first presentation. So you can have either some web service that exposes some endpoints where other services can reach RDF data, but you can also embed RDF directly in web pages, in websites, and usually for that they are using schema.org, which is widely used and common vocabulary that contains many common terms, for example, person, artifact, document, and all the properties that those can have. You can take a look at the website, and they have search, and you can search for your favorite term if you can find it there, and what are the properties of that type. And it's somewhat standardized data representation for the web, for the semantic web. As this is standardized and many websites and datasets are using this vocabulary, they are semantically interoperable. So you can match then different datasets because they are using the same terminology, right? They are using the same classes, they are using the same properties. It also improves search engine optimization and search result visibility. So if you embed such structured data in websites, the indexing bots can then easily get the content and also rank it higher. it also enables then richer user experience, and it also promotes the technological advancements in the web content. So how you can actually do that? There are three ways, basically. First is microdata, and that's one of the two that are directly embedded in the HTML code or HTML document using attributes. So you can have these item scope, item type, and item prop, where we are basically saying that here in this div container you have some item, so that's item scope. The item is of certain type, here person based on schema.org definition, and that person, which is the actual subject here, has three statements with three predicates: name, job title, and email, and then inside the span you have the object, the value. Very similar is in the next one, which is RDFA, and in that one you can see it's almost the same, but here we are using vocabulary, and then we are using these type of n properties, and this is more modern approach based on the RDFA specification. The final one, and also quite favorite in these days, is just having some JSON LD fragment part of the HTML head. So in HTML head you would have this script, and then you have just this blob of JSON LD which describes some entity that is on the website. So for example, if I would be John Doe, software engineer, and I would have my personal web page, I could place a fragment like this, and then the SEO bots and other tools could easily query this information from the website without any need of scraping the HTML. As I said, it's used by search engines, and probably you know Google. And Google uses the structured data from websites to support the search, indexing capabilities, and also to show some more details about the website in the search. You can use these two, but there are of course more tools to check the structured data on websites. So you can open one of those and, for example, try to enter there a link to YouTube video, what are the metadata there, or interestingly, for example, from booking.com page of some hotel or some other accommodation. And finally, you can also build your own tools, of course, that will process such data from semantic web for your project, for your code. And for example, if you would be working with Python, there is a library extract that gives you content of a website, that you give content of the website, and it will parse it and get all the triples that it finds in the content as an output. And then you can work with that as with the RDF graph, make some queries, make some decisions based on that, etc. There is also a curated list of resources for semantic web for many programming languages and many use cases. So if you are not sure where to find some resource, you can take a look there. Maybe you will find the thing that you need. Another thing related to practical use cases, or even like the design of your data sets and ontologies, is persistent identifiers, or are persistent identifiers. We know that we use these uniform resource identifiers or internationalized resource identifiers for resources. They should be stable, and basically they should not change once you assign them, be persistent. You can of course buy the domain name and have some directory structure there, manage the hierarchy and assign things, but you should not change that over time. So there is an issue if you can actually guarantee such long-term, in theory indefinite persistence of URLs. Usually you cannot. You may need to change something and potentially the old one mark as legacy and somehow get rid of the old identifier. So there are services for that, such as v3id or w3id and PURL, persistenturl.org. And you will often see those in ontology definitions, and you can register your namespace there basically and make some redirections. So you actually do not host anything on PURL or w3id, but you just redirect to your content hosted anywhere, and you can change that where you host it, and then you just change the redirect, which will be still the same URL. If you are using such identifiers, they should be also resolvable. That means that they can be used to access the information about that entity. It does not have to be entire web page or entire resource. It can be just a small fragment or part of the website. And this is aligned with linked data principles. So you are linking the data together, and once someone wants to know more about that resource, they use the identifier to access more description about that resource. So this is also promoting the readability in terms of machine readability and actionability. And it supports these semantic web applications. So they are basically traversing through these resources as those are connected through identifiers. Another use case for RDF, which is very practical, are so-called nanopublications. Those are minimum units of publishable information. Potentially it can be just one RDF statement, but it can be also more that are really linked together. And this, as is probably clear, is using RDF technology to capture them. But not just the subject predicate object in assertion, but also to provide some condition when the assertion is valid and what was like the case why it was created, but also the provenance, who and when, using which tool created that assertion. These nanopublications can be sent to some distributed repositories or registries as nanopublication, and the way it works is a bit similar to blockchain. And also it provides then search and filtering, and usually these nanopublications are also signed using private public key pairs. It can be then, of course, verified that it was made by the person who declares the assertion. And the final part is about programming with RDF. So when you actually want to use these technologies in your project and you want to create systems, information systems that somehow work with RDF, it can be either just import-export, but it can be also some internal representation, parsing and behaving based on RDF data. You will need to probably use some libraries, and libraries exist for different programming languages, as I already mentioned again in the previous presentations. They help you with RDF data creation, parsing, querying, traversing, but also some things related to inference, so creating new RDF statements based on existing, and also serialization in various formats. Also, some of these have interfaces for executing SPARQL queries, either on a local RDF dataset, so you basically load the statements and then do SPARQL queries over that, or there are some SPARQL clients that connect to endpoints and run SPARQL queries there. And finally, there are, of course, some libraries for SHACL, these shape expressions, to actually do some validation of RDF and providing the validation report. Now I have a brief examples how to work with RDF in Python. But as I said, there are such libraries for most of the programming languages that you can encounter, and all of them work more or less in a similar way. So you are having some graph representation, you can make some namespaces, and then in this example we are adding 3 statements to the graph. That John is of type person, John has age 30, and John has friend Mary. And these 3 statements are added to the graph, and then the graph is serialized as turtle and printed out of this program. So it then potentially can be stored, for example, to some file. Another example, we can see how to run a SPARQL query. So here we are loading our example turtle file to get the graph to the code. And then we are creating a query. It's a select query where we are selecting name, actually name of each person that we have there. And then we are simply printing out each of these names. Of course, you could here construct more complex queries, different types of queries, get the results in different formats, and then not print them, but for example, do some logic on that. And the final example is about traversing a graph, actually taking a look what is in the graph in some other way than using SPARQL queries. So we here again parse some graph from the file, and then we are going through filtered triples where the predicate must be RDF type. So we are looking for these subjects and objects. Between those is RDF type predicate. And then we are simply printing out that subject is of type O, and O here stands for object. So these are 3 examples how you can easily make some code with. Okay, to summarize not just this presentation but the entire series, I have some recommendations in summary. Basically, RDF and towel technologies are very versatile, flexible, can be used in really a lot of different use cases, from simple ones to really complex and huge and big information systems. And that applies both to academical stuff but also commercial solutions. But as with all other technologies and possibilities that you may be using, there are always some advantages and disadvantages that you should be considering. For example, with these technologies, it can happen that the speed and efficiency of use of resources will not be the best. So if you are taking a look at performance, maybe you will need to compare it with some other solution, for example, with some traditional relational databases and data in tables. Sometimes for some libraries, it's an issue of some community size, availability of proper documentation, sometimes also maintenance, because some of these libraries are not maintained anymore, which causes later on some issues. And of course, you should always take care of stability and reliability of the services built on top of RDF technologies. So sometimes RDF OWL is a really good choice, it can help a lot, but in other cases it can slow you down a bit, it can make some obstacles in development and even cause some serious issues. So you need to really pay attention to these decisions, whether to use or not to use these technologies, and mainly how. So thank you for watching this presentation in this series. I hope the presented RDF technologies were interesting for you. You will possibly use them or at least try them on your own. And hopefully you'll follow up with more on RDF and information systems in the future. Thank you again.